if you try to find the determinant of a diagonal matrix or upper triangular matrix or a lower triangular matrix, all you need to do is multiply the entries in the diagonal. You don't have to do row reduced, you don't have to do the expansion by minors. You just need to look at the diagonal if it is a triangular matrix. So it helps. It's really nice if we can write transformations in terms of a basis that will give us a triangular matrix. Suppose we are in R2. The standard basis, I'll call it S, is 1, 0, 0, 1. Well, suppose I want it in a different basis. Suppose I want to talk about the basis in terms of this set. Let's say I call this 1, 1 and 0, 2. I don't want to write my basis. I want to use this basis instead of that basis because it's a Saturday and I'm feeling wild and crazy. So how do we do that? What's an easy way of doing that? Well, suppose I have a vector, and in the standard basis, it's written as AB. And I want to figure out how to write it in terms of this thing, which means I need to find something times 1, 1 plus something times 0, 2 that will spit out AB. Now this should start looking familiar. I can write this as a matrix. I can say, okay, I have 1, 1, 0, 2. I'm going to multiply by xy, and I want to get out AB. And the way I do that is I'm going to say 1, 0, 1, 2, augment it with AB, put it in row reduced echelon form, and I'll come up with some mess. I'm not going to do it quite yet because I'm going to show you a different way. I'm going to think of this, call this matrix T because I have no imagination and that's the name of the basis. So T times XY has to give me AB. And T is invertible because these are linearly independent. So T has an inverse. And yes, it is diagonal, so that's an unfortunate coincidence that I picked that one. So it has an inverse, so I can hit both sides with T inverse, and T inverse times T gives me the identity. So I will have XY and the matrix T inverse, which I can multiply with AB to get my answer. Now, how do I find the, well, we use Maple to find the inverse, just like we would use Maple to find this. But this is just going to find it already fixed up. But what I want to think about more rather than the gross details. So I have the standard basis, and to get to the T basis, I don't know how to write this, I'm going to multiply by T inverse. And to get back over here, well, I undo what I did, I'm going to multiply by T. Well, what if I have yet another basis over here? We're going to call it W. So W is going to have two vectors, and we're going to squish them together to call W matrix, also the set of matrix. Oh, and everything else space. Well, just like with the T basis, to go from S to W, I'm going to have to multiply by W inverse. And to go from W to S, I'll multiply by the W matrix. So now my question is, how do you go from the W basis to the T basis? Well, if I'm here, follow the arrow, I can go to S. If I do W first, and then I do T inverse, remember we go backwards when we're doing functions because the same thing as composition. And that's how I go from W to T. And to go backwards, I would go from here to here. I would say T first and then W inverse. I'm more interested in you thinking about it in terms of this rather than the oogie notation here. because we can always get Maple to figure out what T and T inverse is, and we don't need to crank those things out. Why might we want to? Well, if I can talk about well, what am I actually getting here? Let me go back. Let's do this example again. Let's say I have V is my vector, is the vector 3, 2, which means it's 3 times 1, 0 plus 2 times 0, 1. T basis is still going to be 1, 1, 0, 2. I want to find T inverse so I can go the other direction. I can do this on Maple, but I want to find how I write this vector in terms of this basis. So I will multiply this by my 3, 2. Three plus 0 is 3. Negative 3 halves plus 1. So negative 1 half. So what this means is if I want to write V, the coordinates of V with respect to this basis, that would be 3, negative 1 half. And that's a good place to stop.